So we are going to talk about the role of performance, and this is the second part of the discussion on performance of processors. So today we will be focusing uh, on comparison of performance between different computers as opposed to finding the performance of one or the other. Because in the previous class we focused on essentially three different aspects of evaluating performance. One was the instruction count, the other was the clock time, and the cycles per instruction, CPI, right? So those three combined, actually multiplied, you got the CPU execution time. So today we'll see if we had certain numbers for different computers, how would we evaluate or average things out? What would be the best way? Homework one has been posted. It's due in a week's time, so that's Thursday of next week. So please turn that in on Gradescope, and we will do activity 4 after our discussion. So recall from the previous class, the calculation for Mips. This is million instructions per second as opposed to the Mips architecture, which is microprocessor without interlocked pipeline stages, which is what we are going to start talking about on Monday. So on Monday, that's when, the nitty-gritty details about machine language and how the instructions should be formatted to be able to run on a particular processor, all the instructions in zeros and ones. That's when we are going to start talking about that. That's coming up on Monday. But so right now we are talking about the Mips, that stands for million instructions per second. So the way you calculate Mips is instructions per second divided by 1 million, 10 to the 6. And instructions per second can be written as the product of instructions per cycle, and we called it, we gave it a particular short form, right? IPC. So that is instructions per cycle multiplied by cycles per second. So your cycles per second is your clock rate. So to indicate clock rate, I'm simply going to use CR. And we know that clock rate is the reciprocal of cycle time. Right? CR equals 1 over TC, cycle time. So clock rate is kind of like the first thing you learn about a processor, right? 2.6 gigahertz, 4 gigahertz, whatever that is, that's the number that first is associated with any processor spec, the clock rate. So you multiply clock rate times the instructions per cycle, the cycles unit cancels out, and you get instructions per second, right? So that's your IPC. And then you divide it by 10 to the 6, you get MIPS, million instructions per second. Now, IPC and CPI are, of course, reciprocals of each other. One is instructions per cycle, and the other is cycles per instruction. Now, when you have multiple instructions, you would have actually averaged that out. So average number of cycles per instruction. So for example, if you had 10 instructions and each of them requiring a different number of cycles, then you would add all of the cycles and divide it by the number of instructions to get average number of cycles per instruction, CPI. So let me just highlight that as well. This is essentially your 1 over CPI is IPC, and then the cycles per second, which is the clock rate, remains as is. Now, if instructions are being used at different frequencies, so 10% of the time, 20% of the time, 30% of the time, and so on, then you would do a weighted average of the cycles per instruction. So if C1 was the cycles per instruction for the first instruction and so on, C2, C3, and so on, then you would find the weighted average, and the weights chosen are essentially the frequencies of usage. How much are they being used to calculate the overall CPI, and that's what would go there. And then you can calculate MIPS based on that. Now, one thing that we are going to talk about today is if you are given two computers with different Mips numbers. So 100 million instructions per second, computer A can do 100 million instructions per second. Computer B can do 100 million instructions per second. Is that the only thing you can use to comment about how fast they are doing things, right? So is that metric enough, or could it be misleading in order to compare computer A and computer B? We'll take a look at that. So coming to our first example, misleading clock rate. Essentially, if you were looking at clock rate, would that information be sufficient to compare computer A and computer B? So on the left column, we have instruction count. So computer A has an instruction set which has 12 billion instruction count, and computer B has 10 billion instruction count. The clock rates are slightly different. Computer A is 4 gig and computer B is 3.6 gig. And the average CPI is the same for both. So nothing to compare over there. Now, when you look at this, you would probably be tempted to say computer A is faster, right? If you just look at the clock rate, which is the reciprocal of the cycle time, it may appear as if computer A is faster than computer B. However, let us try to actually see how they compare by actually evaluating the thing that matters the most, which is what? CPU execution time. So CPU execution time is a very good metric to compare how fast a computer is. So here we will try to ask the question, which computer is faster? Right? And of course, the title itself gives it away. The clock rate suggests, actually misleads us to believe that computer A might be faster, but the story might change after we calculate the CPU time or CPU execution time. So what I'm going to do here at the top of the slide is rewrite my CPU time formula, or the classic equation that we talked about for CPU time, which was the product of three things: instruction count multiplied by cycles per instruction multiplied by clock time. Cycle time, right? So those three things multiplied, you get your CPU execution time. That was what we call the classical equation for computer performance. Now, because we know that clock cycle time and clock rate are reciprocals of each other, we can also rewrite this as IC times CPI divided by clock rate, right? So that's our CPU time. By the way, if you take this and incorporate CPU time in your Mips calculation, you can do that as well. So you can express Mips in several different ways. Let's actually do that. So I'm going to go back here and add a slide after to write Mips the way we wrote, which was 1 over CPI multiplied by clock rate, and we also had to divide 10 to the 6 by 10 to the 6 because it is million, right? This is exactly the same equation as this guy right here. 1 over CPI times clock rate, and then I'm writing MIPS, so I'm also including 10 to the 6. So that's what I have to begin with. Now, what I can do is I can express this same equation as instruction count divided by CPU time multiplied by 10 to the 6, where IC is your instruction count or your instructions per program. Now, just to check whether this works or not, what I'm going to do is, instead of CPU time, I'm going to borrow my classical CPU performance metric equation here, which is the product of those two things, those three things, and I'm going to plug it in my CPU time over here to see whether it matches or not, right? So IC is going to remain as is. I'm going to divide this by CPU time, which is IC multiplied by CPI divided by clock rate, and 10 to the 6 remains as is, right? So I've written IC over here and 10 to the 6 over here. I just made a substitution for CPU time based on the classical equation. And you can clearly see that IC cancels out, your clock rate goes into the numerator, CPI remains in the denominator, you have 10 to the 6, and essentially that ties back into the original equation for Mips, right? So we are trying to put together different ways of computing Mips, how it relates to CPU time. Also, we have seen over here. All right, let's go forward here. All right, CPU time. Let's try to find CPU time for computer A. Let's try to find CPU time for computer B. See whether computer A is in fact faster as suggested by its faster clock rate. So let's do that. So let's say CPU time A equals, what do we have here? For instruction count, I'm going to use 12 billion. And for CPI, I'm going to use 1.2. And then for clock rate, I'm going to use divided by 4 gig, right? 4 times 10 to the 9. So for 4, so this guy cancels out. And you are left with 12 times 1.2 divided by 4 should be about 3.6, and that is in seconds. So CPU time for CPU execution time for computer A works out to be 3.6. If we do the same calculation for CPU time for computer B, it would be 10 times 10 to the 9 times CPI is the same, and we divide by 3.6 times 10 to the 9 should work out to be 3.33 seconds. And of course, you have seen that performance is inversely related to execution time. So if you want to improve performance, then you need to do things faster. You need to reduce CPU time. So after having computed CPU time, clearly it looks like computer B is actually faster than computer A. So that's how, clock rate, if you just look at clock rate, it can be misleading. All right, let's move on to look at some other things that could be misleading. Let's see what exactly do these times represent in the context of a computer, right? So this is the CPU execution time is a measure of the average amount of time it takes to finish a particular instruction from start to finish. So the CPU started working on an instruction, and now it finished working on that instruction. On an average, what is that number in seconds? Right? So that's execution time. So it gives us the measure of amount of time taken to start and finish a particular program. So clearly, smaller the amount of time. If it is less, that indicates it's doing things faster. So that's how it relates to a faster computer. So in terms of metric, right, we use execution time, which is also called as response time. And then the other is throughput. Throughput is a server, for example, working on a bunch of programs called the workload. How much time does it take to finish a given amount of work? So throughput and response time, which is the execution. All right, so misleading Mips and CPI. If you just look at CPI, it could be misleading. If you just look at the Mips or the million instructions per second, that could be misleading as well. So we'll try to ask two different questions here. One is, which computer is faster, of course, but first we'll say which computer has higher Mips. Which computer has higher Mips? I hope you guys agree that a higher Mips value would indicate higher million instructions per second that can be executed by a computer, which means it has to be a faster one, right? Or it might be misleading, but that's one pitfall there. Which computer is has the higher MIPS? That's one question we want to ask. The other is, which computer is faster? Because now we have slightly different values, so that might change. So let's calculate MIPS for computer A. MIPS subscript A. What is that? From our equation, it was clock rate of computer A divided by the CPI for computer A multiplied by 10 to the 6. Clock rate for computer A is 3.6 times 10 to the 9 divided by CPI is 1, and then you have 10 to the 6. So this gives me 3.6 times 10 to the 3 million instructions per second for computer A. And if you did the same calculation for MIPS for computer B, same formula, you would get 3.6 divided by 1.2 and giga here and 10 to the 6 there. So 10 to the 3 should get 3 times 10 to the 3 million instructions per second. So clearly, if you just look at MIPS, it looks like computer A has higher MIPS. So it's able to do 600 more instructions per second compared to computer B. Next, which computer is faster? So if you want to compare, like if you want to comment about faster versus slower, then you look at CPU time. So let's use CPU time for A and B here. CPU time A, same equations. So I'm just going to run through them quickly here. Instruction count for A multiplied by CPI for computer A divided by clock rate for computer A, going to equal 12 times 1 divided by what we have, 3.6 here, should be 3.33 seconds. And then CPU time B, ICB, CPIB, CRA B should be about 3 seconds. So it looks like CPU time or CPU execution time for computer B is so smaller, so computer B is faster. So over here, what does that mean? This means that if you looked at MIPS, your answer would have been different from looking at the CPU time, right? So you cannot just look at the clock rate. In this case, we saw that over here. I can't just look at the clock rate because clock rate over here was better for A, but computer B turned out to be faster. And now cycles per instruction, clock cycles per instruction are actually better for computer A, but computer B works out to be faster, right? So you cannot just base things off of MIPS or CPI. Your best way to comment about faster or slower or comparing performance is CPU time. All right, questions here? Goal is just don't look at clock rate, just don't look at CPI, just don't look at instruction count. You can, oh, and also don't just look at MIPS, because if you just look at MIPS, higher Mips could indicate A, but actually computer is faster in this case for B. All right. Now, let's talk about averaging, because you're going to have multiple times taken for different applications, different computers that are being used at different amounts of time. How do we compare computers when there are so many things at play? Now, in order to have the discussion, first we'll try to see which averaging scheme might work. Because the simplest way to average things out is your basic arithmetic mean, right? Add up all the numbers and divide it by the number of numbers. So that's arithmetic mean. Does it work? Maybe, maybe not. Let's find out. There are other means as well. There is a weighted average mean. There is geometric mean. There is harmonic mean. So let's try to see which kind of averaging scheme might be better in order to compare performance of computers. Clearly, we are starting with arithmetic mean, kind of tells you that it is not going to work. Right, so let's see what we have here. We have computer A and computer B. Still, we have two computers that we are comparing. And it takes 1 second to run program 1 on computer A, and it takes 100 seconds for the same program to run on computer B. So if I just look at program 1, computer B is not doing a good job. Now, if I just look at program 2, computer A is not doing a good job, right? Which is this is a very common scenario. When you have an Intel architecture, when you have an AMD processor, when you have these new M1 chips, they have been designed for certain programs to work really, really well, but certain other programs not to work really well. But if you want to really compare architectures between your Intel chips and AMD and M1 chips, you would have to come up with a better scheme, which looks at a lot more scenarios so that you can then compare things and compare things in a better way. That's where we are going with today's lecture. So if you just look at the average, right, all we are doing right now is adding these two numbers and finding the average. We are not even worried about how often we are running program 1 and program 2. We are just assuming right now that program 1 is used the same amount of time as program 2. That's what we are assuming. So over here you have 1 second, over here you have 100 seconds, you find the average, add them up, divide by 2, you get 50.5. And if you do the same thing for computer B, you've got 55 seconds, right? So it looks like pretty even numbers here. Although if I just looked at program 1 and program 2, it was not pretty even. But because I have some average here, computer A looks slightly better because it's taking about 4.5 seconds lesser than computer B on average. Now, clearly, is this a better comparison? The answer is no, right? Straight away, the answer is no. Why? Because we did not even include the amount of time we are going to be interested in running program 1 versus program 2. What if we are running program 2 90% of the time and program 1 only 10% of the time? And if that is the case, clearly computer A is going to be very, very bad in comparison with computer B because we are running program 2 a lot, right? This particular scheme that we just went through is computing the arithmetic mean. And it's not even weighted. We didn't even weight it. That's one of the main problems here. There are other problems as well. We'll talk about that later. The way you find the arithmetic mean, if you had over here, you just have two numbers. But what if you have several programs, right? I programs. Then you sum up the time taken for each of these programs. You sum up all of them and you divide it by the number of programs, small n. Right? Let me just put that here. So this guy and this guy. Time to execute ith program. And this guy is the number of programs. And we'll follow this later as well. What is this calculation useful for? It is not, especially for uh, finding things as far as comparing performance is concerned. It is not very useful. It could be useful when you have programs that are not preferential, like you're not preferring to execute one program or the other. Then you can get some sense of comparing the faster computer. So it only works in some special cases, not for all. The next averaging scheme is a weighted arithmetic mean. Now we are including the time, the fraction of the time we are executing program A and program 1 and program 2. So still it takes the same numbers, right? So we are consistent with the numbers here from previous table. 1 second, program 1 on computer A. 100 seconds for program 1 on computer B, and so on. But we are running program 1 a lot less than program 2, where actually computer A is far behind. So if I looked at this, my guess is that if I average things out here, computer B should be very far behind, right? So let's actually see whether that works or not. So how is the weighted thing going to work? I'm going to find the weighted average, arithmetic mean, weighted arithmetic mean for A and B. If I did that for A, for example, I would get 10% of the time I am running for 1 second, and 90% of the time I'm running for 100 seconds, divided by 10% plus 90%. So that's just 1. And that would be 90.1, right? So weighted arithmetic mean for computer A is 90.1 seconds. Let's do that for computer B as well. Weighted arithmetic mean for computer B is, so if I did that, 10% times 100 is 10, plus 90% times 10 is 9, and I divided that by 1, so that comes out to be 19 seconds, right? So it looks like computer B is doing things way faster than computer A, which is kind of what we expected. We are running the program 2 for 90% of the time, where actually computer B wins, right? So this is probably a better scheme, at least if I compare it with the arithmetic mean. However, there is one big problem with weighted arithmetic mean, which is if I change the calculation by normalizing to computer A or normalizing things with respect to computer B, the numbers could be different. We will take a look at that example coming up. But the general formula for weighted arithmetic mean is to simply add up all the weights, those are percentage of the time that each program is being used for, multiplied by how much time does it take for that program to execute. I indicates your program itself, ith program, where the addition of all the fractions should be 1. So it depends on the relative use of these programs, right? So clearly, when we did this over here in the previous slide, we got 90 here, we got 19 here. So that essentially tells us that how much do you use these programs, it's going to depend a lot on that. That is literally Arm's law, which we looked at earlier. if you are going to improve certain aspect of your computer design, the factor of improvement is going to depend on how much time you're actually using the improved part. If you improve something and don't use it very often, then you don't really gain much. That's exactly what this is talking about. That's the law. So let's see if we can do some calculations using the Armstrong law. Let's see if we can improve performance by a certain factor. So Armstrong law, what does it say? It says when you improve certain aspect of a computer, you also have to use that aspect in order for you to actually gain something from it, or overall improvement to be present. So improving an aspect of a computer and expecting a proportional improvement in overall performance is not going to be true. And what happens is, if you improve one aspect and you expect that, okay, so I'm going to improve the clock rate. And if I improve the clock rate, if I assume that my CPU time or the overall performance is just going to improve by the same amount proportionally, then that's not going to work. It's not going to happen. So that's a misconception that we are going to take a look at with this example. The Armstrong law can be written up in an equation form, which is the time of the improved execution is equal to the time for which it is affected. So if you improve certain thing, you might not improve that for all the time. It might be for some affected time, divided by the improvement factor plus the time for which it wasn't affected at all. So let's suppose it's better understood with this particular example. We have a computer that is trying to do some multiplication operations. And it turns out that multiplication operations account for 80 seconds out of 100 seconds. So a particular program gets done in 100 seconds. But out of that 100 seconds, 80 seconds it spends doing multiplication operations only. So the question here is, how much improvement in multiplication operation should be done to get 5 times of overall improvement, right? So if I improve my multiplication operations, if I make my multiplication operations faster and faster, can I somehow improve the overall performance by 5 times? What does that mean? Overall 5 times it should improve. Well, if it was taking 100 seconds, if you improve it by 5 times, now it should take 20 seconds, right? So let's say, so your improved time is 20 seconds. What was your affected time? Well, we were only focused on improving multiplication. So your affected time was 80 seconds, right? We were only running multiplication for 80 seconds. That's 80 seconds. Just leave it as S. And then we were after some improvement factor. That's exactly what we want to find out. How much improvement? So this is the X. I don't know that. How much time is unaffected? Well, if I have 100 seconds total, 80 seconds I'm improving, 20 seconds is unaffected, right? So this would be 20. So if I plug this in, I get what? 20 equals 80 divided by X plus 20. What is X? You guys see that? 0. Yep. Which means you can do it. No matter how fast you make your multiplication operations to work out, no matter how improved your multiplication algorithm is, you cannot just improve multiplication to get a 5 times overall improvement. You guys see that? So for that to work, you would need to reduce this, right? let me pose that question to you. Can I reduce this 80 seconds to maybe 60 seconds or maybe 40 seconds and get that improvement? Well, so these two guys cancel out, right? So 80 over x equals 0. Right. But you can't get that. Your improvement factor is infinity. You're right. X is infinity. Yes. So no matter how much you improve your multiplication operations, you're not going to be able to get that 5 times overall improvement in system performance here. All right. So now let's talk about normalizing things with respect to programs for a particular computer. What I mean by that is, instead of just looking at the time it takes to execute a particular program on computer A, I'm actually going to look at normalized times, and I will normalize them for with respect to computer A first, and then I will normalize them for computer B next. And if I did this and used a weighted arithmetic mean, the question is, will I get the same answer no matter which computer I used to normalize or not? That's the question. And right now I'm ignoring the fraction of usage here. So I'm ignoring that program. I'm assuming that program 1 and program 2 are being used for the same amount of time, 50-50. So that keeps my calculation pretty simple. These are again the same numbers as we have seen before. Program 1 computer A, 1 second. Program 1 computer B takes 100 seconds and so on. Now, if you normalize things with respect to computer A, what numbers are you going to get? Well, for program 1, computer A takes 1 second. Computer B takes 100 seconds, so 100 times more. So if you were looking at normalized times, for A you would get 1, for B you would get 100 times more. And similarly, if you look at program 2, here you have 100, here you have 10 times less. So if this is 1, this would be 10 times less, right? So that is, those are numbers when you normalize your execution times with respect to one computer, right? Why is this important? Why is this normalization important? Well, if you think about comparing any two processors or a bunch of processors, then a good way of going about it is to have a reference computer so that you know how fast or slow that reference computer is, and you can compare every other computer to that reference, right? So that's why we need like a reference, a normalization. So we are trying to look at how effective is arithmetic mean when you use computer A as normalizing computer or reference computer versus computer B. What you would want is, no matter which computer you use as your reference computer, they both tell you that the same computer is faster. Let's see if that happens or not. So you saw how the numbers work out for normalized to computer A. Let's also do that for computer B, right? So when you normalize things to computer B, these two are 1, but this is 100, this is 100 times smaller. This is 10, this is 10 times bigger. So if this is 1, that is going to be 100 times smaller. And if this is 1, this is going to be 10 times bigger. Now let's do the weighted arithmetic mean, or in this case, just the arithmetic mean, right? So what are we going to get? I'm going to get a 1 over here, 100 plus 0.1 divided by 2, that is going to give me 50.05. And then I have 10 plus 0.01 divided by 2, I've got 5.005. And then last column is 1. Now let's take a look. If you just look at these two numbers, which computer is faster? A is faster because this is taking 1 and that is taking 50.05. If you look at this, what is the story here? B is faster, right? So that means that if you used arithmetic mean or weighted arithmetic mean, you would end up into a problem because depending on your reference computer, things might change. You would get a different result for the faster computer, right? So that's a problem here, right? So they're different. That's a problem. And need better averaging scheme. Arithmetic mean or weighted arithmetic mean is not doing a good job as far as normalization is concerned or referencing is concerned. Okay, let's do geometric mean. See if that works out. What is geometric mean? Well, you multiply the execution times and you take a square root. Or if there were 3 computers, then you would multiply x1 and x2 and x3, and then you would take a cube root. Sorry, not computers, I should say programs, right? So each one is the ith program. It's indicating each program. So either I take a square root or a cube root or the 4th root or the nth root in general. I can also express geometric mean using an exponential and a log relationship. It's the same equation. So let's see with the same numbers whether we get a consistent result or a different result. So I have the same values for program A. We also have the normalized values here for program 2. Arithmetic mean from before. Now we are going to populate the geometric mean. So I have 100 here and a 1 here. Multiply them, take a square root. I got 10. Then you have 10 here. You multiply with 100, take a square root. You got 31.623. Now you start working on the normalized numbers. 1 times 1 square root, I get 1. 100 times 0.1, that's 10. Square root of 10, 3.1623. Right? Let me highlight the numbers I'm using here. Using that and that to get that. I'm using that and that to get that. I'm using that and that to get that. Using that and that to get that. You guys get the idea now. All right, next, what do I have next? 10 times 0.01, so that would be 0.1, square root of 0.1, 0.31623, and the last one is 1. So let's zoom in, try to compare which computer is faster based on normalized to A. A is faster because it's taking less time. Now let's talk about normalized to B. Which one is faster? A again. Oh, A, right? Yeah. So geometric mean is particularly useful because it works for comparing execution times for multiple programs. It's actually the metric that you use in current comparisons, right? So it's not just theoretical. This is the one that is currently used based on Spec 2017. I'll talk more about the standards in a little bit. A key property for geometric mean, in case you run into this when you're doing some numerical problems, the geometric mean for certain sequences, if you have two sequences, for example, you have xi and yi, and you wanted to find out the geometric mean, there is a relationship between them. That is, the geometric mean of one set of observations divided by the geometric mean of the other set of observations will equal, you divide the observations first, element wise, and then take the geometric mean later. So let's try to summarize these performance metrics. We had arithmetic mean that worked kind of only for special sum cases, but geometric mean worked pretty well. But the geometric mean, when you weight the geometric mean, that's what works really, really well. So you used arithmetic times essentially when there was not much, the fraction of the time for which the instructions were being used was not that different, right? So the use of for times, the number of instructions, for those kind of things, if you use arithmetic mean, you are fine. You would be okay. But you would not be able to use that in order to compare CPU times for different computers. Geometric mean can be used to compare ratios. We will see in a little bit that there is one particular number we would want to compute as the number for a computer, and it would be a ratio. It's called Spec Ratio. So if you have different computers, different programs with different spec ratios, then you can use geometric mean to find the faster computer. Right? This is geometric mean of the ratios. Or in general, you can do the weighted geometric mean, where you're actually using the fraction of the time as well as the advantage of using geometric mean to remove the effect of normalization. That leads us into benchmarking. And you hear this term a lot whenever we try to compare computers, right? Whenever a faster computer or computer architecture comes out, we hear, okay, how does it fare with respect to some benchmarks, right? And the reason why we need to talk about benchmarks is because it's a multi-level problem. Now, when a user is using a certain application on a computer, the user is way over here. They are interacting with the application itself. But there is a whole set of layers the computer is using underneath the application, starting from programming languages, compiler, the instruction set architecture, data path and control, the functional units, down to the nitty-gritty transistors and wires. But at each level, you have a different performance metric, right? So if you are just looking at application, you are looking at things very broadly, right? How many answers per month can I find out? How many useful operations per second can I perform? As you go down this list, that becomes narrower and narrower. For example, if you go down to the instruction set architecture, then you are going to be talking about how high is the Mips, million instructions per second, or how high are the millions of floating point operations per second. That's instructions, that is floating point operations. And if you go down, then you are looking at megabytes per second, cycles per second, or clock rate, right? So clearly this is, at each level, it's a different thing that you're trying to compare, right? Each metric has a place and a purpose, but each can be misused, right? You could optimize anything for a special case, but that doesn't give you the whole picture. which is why we need to use benchmarks. But they also come with some pros and cons. So when you're trying to do benchmarking, you do full application benchmarks, and you have operating system benchmarks, and you have micro benchmarks. At each level, you have certain benchmarks in using which you can compare one computer system to the other, right? How efficient is the computer design? If you want to talk about that, then you need to do benchmarking at every level. The pros and cons of each set of benchmarks. For full applications, the pros of benchmarks are it's portable and it's widely used. You see this, sometimes people say, all right, how is this particular program or this particular application performing? The con is it is less representative of what is underneath because it's running way at the topmost layer. Now, if you go down to the operating system, which is kind of in the middle of all the applications and users and the actual hardware, the operating system benchmarks are actually easy to run because they can be hosted by your local operating system, but they're also easy to fool because it is sort of a manager for all the CPU schedulers. So you can twist the kernel benchmarks to kind of get the numbers that you would want. But if you go down all the way to the micro benchmarks, how fast are things working out? Then you can actually identify the peak capability. You can actually identify the potential bottlenecks. One problem with that peak capability is peak may be a long way from apps performance, right? So this is talking about how do those instructions get executed all the way down at the micro level. However, that might not indicate what is happening. So that might not give you the best assessment of the application's performance. So the benchmarks are, a good way of assessing computer performance at each level, but they also come with their own pros and cons. Now let's talk about something that is very widely used to compare processors. And right now, at least in the personal computer market, the new Apple M1 chips are kind of crushing it, right? And the reason why they are crushing it is because their spec CPU numbers, not just for CPU, but also for other subsets of spec, they are very, very good when you compare them to their Intel or AMD counterparts. Let's try to take a look at some, by the way, so spec, it started in '89, and they had a particular workload of programs that was called Spec 89. After that, there were a couple more changes to spec. Spec actually stands for Standard Performance Evaluation Corporation, right? So this is something that you computer manufacturers subscribe to essentially get the standard workload or bunch of benchmarks. They would run it on their computer and provide the execution times or spec ratio. And this is done not just for CPU, but for IO, for web, for cloud computing. Now there are lots of categories. So, I would encourage you, if you're interested in this, just go to spec.org and you will see there's a lot of information there, but at least you can get a sense of what are the different categories of comparing performances of computers. The one that we are going to talk about is the spec CPU benchmark. To compare performance, we are going to look at this benchmark with respect to one set of programs, an actual workload. Workload is a set of benchmarks that are commonly used by computers, by users actually. So we're going to take a workload, we are going to run it on computer A, B, C, and so on. We are going to see who does a better job at it. But as a reference, as a normalization, we are also going to run the same set of workload programs on a reference computer. And then we are going to find a spec ratio, and the geometric mean of all the spec ratios is actually the one number you would use as the identity of the performance of a computer, right? So users don't like to read spec sheets. with bunch of numbers, you would just want one number and that's it, right? One number, tell me the story in one number. Higher the number, you would say, all right, it's better than that. Lower the number, you would say it's worse than that. All right, so this is the table I'm going to show you guys in just a bit is actually the Spec CPU 2000, right? So those are the previous version. Right now we are looking at Spec 2017 right now. So 3 years ago there was the last the change. The most recent one is from 2017. The set of benchmarks and all the computer vendors, their results, they were last done in 2017. So if you have a new computer architecture, you would subscribe to that Spec 2017, get your programs, run them on your computer, and you would give your numbers to Spec to publish. Okay, so let's go down this list here. We are trying to look at elapsed time to execute a selection of programs. That's what we called as the workload. We are going to make sure that we have negligible I/O so that all the focus is on how much time is being spent on the CPU. We are also going to normalize things with respect to a reference machine. But after we have all the numbers, we are going to use geometric mean, right? So we are going to take the nth root of the product of the execution time ratio, also called as the spec ratio, for all the programs. This is the spec ratio. And you compute spec ratio for each program on that computer. And then you find the geometric mean of that. In 2006, we had 12 integer-based programs. That was the integer workload. And there were, I think, 17 floating point programs for the floating point workload. I'm not sure about the 2017 numbers. You guys can check on that. 12 integer. And I think it was 17 for floating point. Because you would want that list to be not too small, not too big. So depending on the program, it can fall in one category or the other, right? So when you have applications that are using floating point numbers, then you obviously have those floating point benchmarks. But for integer applications that use integers, you have integer benchmarks. Let's take a look at the numbers for the Intel i7 processor. This is again from 2006, and it is only looking at the integer benchmarks. There are 12 of them. It can go from, let's take a look at the programs that is considered as the, or I should say selected as the 2006 integer benchmarks. What kind of programs were there? There was a chess program, chess game. There was a Go game, AI-based Go game, C compiler, block sorting, Perl, your string processing program. What else? Video compression, very complicated quantum computing simulation. So a variety of programs. And the goal is to kind of get kind of a diverse group of programs. Now, we saw earlier that when we were trying to compare computers, we were looking at CPU time. We are not trying to look at clock rate. We are not trying to look at Mips. We are not trying to just look at CPI. We were trying to look at CPU time. And for CPU time, it was the product of instruction count, CPI, and the clock cycle time. So if you multiply these three, you should get execution time, also called as the CPU time, in seconds. So for each of these 12 programs, benchmarks, integer benchmarks, you have these numbers for the Intel i7 architecture. x88 was the best, sure. So let's see, you might take this guy, you multiply them, you get your execution time, and you fill this list, right? So you have instruction count in billions, cycles per second. By the way, if you notice, the cycles per instruction are very different, right? So it can, the lowest number that I see on this list is what, 0.6? Right, 0.6 cycles per second, cycles per instruction. And it goes as high as 2.66, right? So the cycles per instruction also can go, can be very, very different for different programs. Then you have clock cycle time in nanoseconds. You multiply the three of them, you get execution time in seconds, because the billion here and the nano there are going to cancel out. Then you have a reference time. What is that guy? Well, the reference time is essentially the time it took for that program to run on a reference machine, right? So of course, we are going to take a reliable but slightly maybe poor reference computer, right? So that's why your reference times are pretty high when compared to the execution times. The point which I do not know why is considered as a common right by. Well, I wouldn't say everything is like a common program. Some of them are not so common as well. But this is the set of programs that was for 2006. I'm not sure how the 2017 set looks like. Maybe you guys can check that and let me know. All right, so you have got execution time over here in seconds for the computer under test. And then you have got the reference time as the execution time for the reference computer, right? Same reference computer for all the benchmarks. What you do is you find a spec ratio. Spec ratio is essentially the ratio of reference time to the execution time. So you divide this guy by this guy, you get that. Divide this guy by this guy, you get that, and so on, right? So let me just write this down here, spec ratio. And this is for each program. Reference divided by execution. And then this execution time is for this Intel core, and this guy is for a reference machine. Now, would you want the spec ratio to be higher or lower? Higher, right? Yeah. So if the spec ratio, you see this, you want that reference machine to be left behind, right? So you would want that reference machine to be, that time, the reference time should be, you would want that to be very, very slow, very, very long compared to the execution time for our machine. So you would want this number to be as large as possible with respect to this number, right? So you would want this guy to be as large as possible. The bigger it is, the faster your machine under test is running with respect to the reference machine. All right. So you would want that spec ratio to be as high as possible. All right. Higher the better. Let me just write that down. High is good. All right. A pun not intended. All right. Let's see. At the bottom here, we have 25.7. What is that? That is the geometric mean of all the spec ratios. So if you took all these spec ratios and you ran them through this particular formula to compute the geometric mean, you would get essentially one number, right? Like that's the one number you would identify the performance with for a particular computer, for a particular processor. Now, the bigger the number, the better it is for you, right? And this goes on a publicly available database. It's on spec.org, right? So all these computer manufacturers, they are trying to come up with a better number so that they can attract customers. But for Intel iCore 7, that was 25.7 for 2006 integer-based benchmarks. All right, I hope that discussion was helpful. Now let's talk about another benchmark here. This is the spec power benchmark. So of course, as what happens what is the byproduct of increasing clock rate, right? So one of the things that the computer manufacturers do, and they did a pretty bad job with Pentium 4 with this, is they tried to push the clock rate up, right? And they think that, all right, if the faster my clock rate, I will be able to execute more and more instructions in a smaller time. But the problem with that is you will run into a power wall, right? You will have a lot of heat being generated by those processors by increasing that clock rate, right? Which is why after Pentium 4, the increase in the clock rate kind of went down actually a little bit. It didn't go up because it was so bad in terms of the power benchmark. Now, and there are other related topics about that as well, because now you're talking about using 4 cores or 8 cores on a chip. How are you going to balance the usage of each core in order for that heat to also be synced? Like all that power also needs a cooling system in order to keep going. All right, so we have a power benchmark. Let's talk about what this is. This is essentially the assessment of power consumption of the server at different workload levels. So what you're doing is you are assigning a workload. So 100% workload means you are giving it a lot of tasks, and then you're doing different workloads, right, at the server side, as opposed to doing this at the client side. So on a server, which is trying to execute as many number of programs as possible in a given amount of time to increase its throughput, you're going to see how is the power consumption at different workloads. And the performance metric we are going to use is SSJ, server side Java operations per second. So this is specifically doing Java operations. This is server side Java operations per second. And then at each workload level, we are going to see how much power is being consumed. And the way we find this benchmark of overall server-side Java operations per second per watt is by simply adding up all the server-side Java operations per second to the amount of power that was consumed at each workload level. So add up. In this case, we are doing it, from 100% down to 10%. That's why you have, 0 to 10. So 190. So you're going down by 10% each every time. At the top, you have operations per second, and in the bottom, you have watts. So you're trying to evaluate this particular metric. Operations per second per watt. So this is the spec power benchmark. This is the 2008 benchmark for Xeon X5650 chip. You start all the way up here, 100% workload. They are 865,618 server-side Java operations per second that are supplied to, or that's the workload for that Xeon processor, and it is consuming 258 watts. You go down 10% at a time. Of course you're going 10% at a time, so there's a reduction in the operations per second because you are making things easier for the processor at any given stage. And as you would expect, even the power consumption should go down because of that. And at the end, you do an overall sum of all the operations per second and the overall wattage. You divide one by the other to get your power spec. So, would you want this number to be higher or lower? Right, high. So you would want to have higher performance and lower power consumption, right? So you would want that ratio to be as high as it can be, and that's your power benchmark. Now there are other benchmarks as well. If you go to spec.org, you can see that they've updated quite a bit since 2006. So take a look at the numbers, and if you're interested, take a look at why the M1 chip is so attractive nowadays. All right, so let's do the activity now. I'm gonna stop recording here.